Thank you very much for that great introduction and zooming out of the issues around education and delivering it around the world, and obviously particularly with respect to maths. And that's given a very interesting beginning perspective, I think, to the summit. So I really had a number of objectives in this talk. I want to go through the vision that computer-based maths is. Now, many of you are aware of that. I want to just recast it, make sure we're all on the same page so we know what we're talking about, and hopefully add some pieces to that as well. I want to talk a bit about what I think the issues are in making these changes. And I then want to go on to say where we think we've got to so far, and, want all of the suggestions and how we can move that forward. And of course, all the way through this, I may only have half of the issues, and I want those bulked up by everyone who's here. And finally, I want to talk about real actions that we can get out of the summit and things that we can move forward at the end, and how we focus it. So those were really the objectives of this session. And let's just talk about what I think is the central issue here, that we have two kinds of maths in the world. There's math that is in the real world, that is a problem-solving subject, that is important as it's never been in the world's history, to every aspect of our lives. And then there's this math in school that's completely or increasingly disconnected from that. And it's that difference in the subject matter that I think is the focus we absolutely need to be on as we talk about this. And I want to describe a little bit, let's zoom out a bit and talk about exactly what makes those things so different. One of the things, by the way, I do think is good at the moment, before I get into that, math is also high on the agenda as it's never been before. Right? People care about math. You stick something in the press about math, and there's lots of stuff that comes up, plus or minus, about it. People care. That wasn't true 15 or 20 years ago in the same way, or in past eons before that. So the bad news is that what we're mostly talking about, in my view, is 80% the wrong subject. So we've got the presence, but we haven't got the content correct. Let's go back through the discussion a bit so everybody can hopefully get on the same page and understand what we're talking about here. Why are we learning math? I think there are three primary reasons for this. Technical jobs that are so important in pushing our economic success and, in many cases, individual social success and so forth forward. What I call everyday living, making sure that all of us can function in a society. This is a much harder quantitative problem than it ever was before. Just to survive in any society, whether developed or less developed at the moment, you need a lot more quantitative skills than you ever did in the past. And thirdly, what you might call logical mind training. The ability to think logically about situations. The way I think about this is maths, to my mind, is, in a sense, one of the world's greatest problem-solving systems. And we need people to feel that. We need people to be able to get that, because when you do that, it really helps you in all areas of life. Let's talk about what maths really is. So maths, in my view, is a four-step process. You start with the question, what is it that you really want to answer? You then take that from the real world into math, into the formulation of math, this really powerful language. Step 3 is computing. You go from the question to the answer in a math form, and step 4 is you go back. Did I answer my question correctly? The crisis at the moment is that we are spending perhaps 80% of our time teaching people to do step 3 by hand, when that's the one step computers can do better than any human. What we should be doing is using computers to do step 3 and using students much more for steps 1, 2, and 4. Those are the critical things that we need in order to succeed and for students to succeed in problem solving. Now, one of the keen things that I wanted to do and I wanted to announce today was we have been trying to work out a way to visualize those 4 steps in a meaningful way that people could really get hold of. They could visualize in their head what they're doing. One of the problems I've had in describing this, and shocks actually, is how little people understand what they're trying to do in math altogether. And I think that's a key problem in their adoption of it. So we have what I call the CBM solution helix of math. And the idea is that these 4 steps, question, translate to math, compute, and interpret, are represented on this helix. Now, in fact, it's not quite as simple as just going around this once, because sometimes you have to go around it several times. When you get to the end and interpret the answer, you actually need new questions and you need to go around. And hopefully, though, eventually you kind of reach for the real result that you wanted. So I'm hoping, and you'll see after this, we've made a poster of this, which I hope will hang in many places in the future. So I hope that we want to give people visualizations of what they're trying to achieve when they do math. So the key thing here is math is a much bigger, broader subject than calculating. Calculating by hand is a piece of machinery that is an important, the calculating element is important, but we don't have to, we should use the best machinery we can for that. And STEM, as in science, technology, engineering, is a much bigger subject in many ways than math. Math is a structure for that, and as well as a subject in its own right. And I wanted to sort of relate the issues between these various pieces in some different way. So one of the things I think is important to understand is the difference between the mechanics of the moment and the essence of a subject. And many people have told me this is not just true of math, but it's very predominant in math right now. So here's what I mean by this. When you look at a subject, the question is, you have to learn things, you have to learn ways to actually do that subject at this moment. But that's not necessarily the essence of the subject. So in math, for hundreds of years, the sticking point in applying math was calculating. You couldn't get the calculating done because there was too much stuff to do. You couldn't apply math in many cases because the calculating was too hard. That got fundamentally changed. Computers automated the hell out of calculating. You could never imagine any bigger automation change, bigger mechanization of any subject than computers have brought to calculating. So the essence of the subject is problem solving. Math is there to solve problems. It's a system problem solving. The mechanics of the moment, it was a very long moment. The key mechanics of the moment, we're doing it by hand for a long time, but now that's changed. So we've got to therefore change what we're doing with the subject. An analogy I often use is photography. It's a useful, a recent thing. I often say if photography was a mainstream subject in schools today, I think we'd be starting by explaining how to load films into cameras. Or in fact, you know, coat plates with glass plates with chemicals. You know, those were the mechanics of a particular moment of photography. I don't think they're the essence of photography. The essence of photography is a creative way of representing the world in some sense. Now, today's mechanics, you always have to learn something of today's mechanics as well. You know, what we're doing with computers today, how we code, that's today's mechanics. So, and in 20 years' time, those will have changed somewhat. So it's not like we don't have to learn any mechanics. You have to learn some mechanics, but it should be today's mechanics, not yesterday's. And I think we've got to distinguish those very hard when we talk about things. Now, when you talk about the calculating, one demo I like to show is, you know, this is a piece of equation solving many people would do at school. It's simultaneous linear equations. But the essence of this thing is we're setting up a problem using equations to represent a setup. You know, this is a problem we might have. Equations are a good way to represent that. But you know, what I've done there is actually very similar to this, right? It's just the mechanics are a little different. That happened to turn up with the cubic equation. Yet that's something that most people after 10 years of schooling aren't able to do. Why? And in fact, it's even worse than that. You know, network willing, I can talk to my phone and I can say, solve x cubed plus 2 equals 2y and y minus x equals 5. Now, we never quite know whether... Okay, so I think we got an answer to that. And let me try and put it in front of the camera. I have spoken to my phone, and I have got through Siri a representation that most people can't do after years and years of schooling. Right? You've got to ask why we're training them to do that, as opposed to the much bigger picture that they could be doing. Now, one of the other things I think has gone wrong is when you look at most of our curricula, they're based around mechanics of the problem, the inside, what's happening on the inside. you know, inverting matrices, simplifying surds, whatever that is. I did know at one point. What we should be doing is what we call problem-centric maths. So take the problem that might be of interest to the student and work from the problem. Use the math as a tool for solving the problem. Use the computer as a tool for doing the math. And you know, this is some examples. Design a currency, make a perfect password for your login. What's a beautiful shape? That's a perfectly relevant thing to ask. You know, here's an example where you kind of need a computer. How much can I compress a photo or video by before you notice? Well, you can actually try it in real time and see what happens, right? I mean, these are key things that you can do. You know, I can't do this by hand, right? It doesn't make any sense to do this by hand. It doesn't work. One of the things that I think is important also is to distinguish what people might find interesting in their own right from what we are essentially forcing the world's entire population to do. So here's what I mean by that. You know, ancient Greek was a subject I quite enjoyed. And, you know, I think people who get excited about ancient Greek should go on and persevere as much as they can. I think, by the way, the modern age of computers allows you to do that much more than you could in the past. You can go down your own interest and pursue things. But I wouldn't force the entire world's population to learn ancient Greek, because I just don't think, you know, for 10 years of their lives, because I don't think you can justify that. And my calculation is about 21,000 average lifetimes per year is spent learning hand calculating and maths. So that's a lot of human endeavor. We better be damn sure we know why we're doing that. Another thing that frustrates me sometimes, and I think is interesting to discuss, is the argument that is sometimes proffered by some of the maths community occasionally. And I always feel like they should apply logic to their own maths logic to what they're talking about. So, you know, I tried to write a little thing. If math is for all students, it implies that maths in education must be pretty connected to most people's real world life and maths in the real world. And that sort of implies that maths in education matches what we're saying in CBM. If you're going to claim maths is a specialized subject for its own beauty because it's good for you, you're back to ancient Greek. So it's not a bad subject. I think it's great that people should get excited about that subject. And we should encourage people who are excited to continue. But that isn't the world's general purpose subject that we're talking about that we need to fix for everyone. And I think math, by the way, is justified across the whole world for everyone, but only if it's the right math. So one of the things I'm saying is maths, today's maths is essentially a proxy for real maths. And one of the things that in places like the UK, people used to have classics that they learned at great detail. Now, classics was clearly a proxy for something because people didn't speak Latin every day. Maths, we have a real subject there called maths that we're using in real life, and it's more important than ever before. Why are we teaching a proxy to that subject rather than the real subject as it is today? So one way to look at this is maths, essentially, is a system for doing STEM and for doing life. You know, the fact that you think mathematically allows you to problem solve and think about life generally in a somewhat different way and a very productive way. And I think that's some of the reason why all these surveys that show people who have studied math do better in sort of economic and other terms in life, I think that's why. They have a way, a structure for problem solving. And while we're about it, let's talk about coding. Coding, I think, is a way to express math. It's more important than many of the recent excitement about coding thinks. It's not just about computer science. It's a language for expressing math in the modern world. And another way I sometimes describe coding is the difference between, you know, if you're composing something, it's sort of the relationship between composing something and English is sort of the relationship of coding to math. It's the way you express yourself in a mathematical way as you write code. So the math that I'm envisaging is both more practical and more conceptual. It's both. That's a rare opportunity. We don't have to pick between the vocational and the intellectual. Math in the real world is highly conceptual and intellectual, as well as being highly applied. So those two can happen simultaneously and should. Another thing that I've only more recently understood is the extent to which removing the computer in most places around the world removes the context. Maths wasn't applied to many things it's today applied to before computers, because it didn't work. Now, the fact is it didn't work for high-level biology. The things were too there was too much noise in the computations. You couldn't do it. A lot of data analysis. You couldn't do it. It worked well for pieces of physics. It worked well in various pieces of engineering, right? So we've got to be clear. Math wasn't very applicable to many areas of life before computers. So guess what? If you remove the computer in education from math, you are going to remove any or much of the real context that you could have for that math in education. So it's no use setting biology questions. And so then people see that that context isn't there. They think it's disconnected from the real. They don't understand why they're doing a biology question that has nothing to do with anything in real life because it's so disconnected, can't have real data in it. Doesn't make any sense. But people never use math for that in that case. So we are removing the contextualization from math by removing the computer in many, many cases. You know, I don't understand why we don't teach calculus to 5-year-olds. Right? Calculus is a very natural thing. I don't understand why we don't teach, you know, primary school thermodynamics. Actually, you can get quite a lot of understanding. You know, when you make the container smaller and you push the stuff together, you know, you'd expect the pressure to go up, et cetera, et cetera, et cetera. What I'm talking about centrally, to be clear here, is computer-based, not just computer-assisted. So what I mean by computer-based is the subject in the outside world changed because computers came along. That's different from history, for example. History is a subject that I think has evolved over time. Well, it's evolved in several senses over time, actually, history. But it's a subject that's evolved, and you know, you would do it in a slightly different way with computers. I don't think it's fundamentally changed because computers exist in the real world. Maths has. It's a different subject. So what I'm talking about here is the subject has changed, and there's also the layer of how you deliver the subject, the computer-assisted. What a lot of people are focused on is the assistance, not the subject. And we've got to do both. And we need the computer assistance to deliver the computer-based maths. So in a sense, that's a sort of outline of what's the vision and how might we go about thinking about this reform. Let's talk about the elements of making this change and what we see as sort of key in those elements. And you know, again, this is something very much open to discussion during this conference. And I hope you'll contribute more of these elements. So one which is clear is making clear what the vision is for the right subject. And I think there is a lot of confusion, and we have often failed to do that well. Another thing, I think, is building the right subject. So you got the vision. What's the manifestation of the vision? So that involves a bunch of things: defining outcomes. Which bits of math are you really talking about? And it's surprisingly multi-layered. And also what the narrative is that surrounds that. Those are all parts, in my view, of building the subject. Another crucial thing is aligning assessment. You know, I'm not a great fan of how everyone has to be assessed on everything all the time, but I can't see how one gets rid of that at some level. But what we can do is make sure it is vastly more aligned. And alignment to me means some number of things. It has to be open-ended. That's what life's like. It's obviously got to have a computer in it because that's what life's like. And you know, there are many other alignments one can talk about. And another thing which is, you know, I put in a rather business-like way is I want to fix math marketing. Right? I mean, the marketing of math is just about as bad as it could possibly be. I mean, not to make too clear which country this is, but you know, on releasing a new maths curriculum in my country, you know, at the top of the press releases, we're going to make sure people can do long division well. Now, whatever you think about long division, it's clearly not the thing to market about. Your great result from primary education is the most exciting thing you were doing was long division. So now I wrote a blog post about is long division the pinnacle of primary math education? So we got to make sure people are seeing things that are exciting about math, and we're pushing that out there rather than always making it seem like it's a hard and upsetting slog through life. So one of the things is we put up a new website today, and we were keen to explain. I rather like our sort of guy reaching for infinity here. And so in this, we were trying to explain, you know, using maths in infinite ways to improve life reaches way beyond traditional things. We're trying to explain what's good about, you know, a CBM student. And at the same time, I guess, we're trying to, here we go, there's the proper animation happening. At the same time, we're trying to explain kind of what's wrong with the traditional math of today. The guy's kind of bowed down. There are all these math symbols raining on him. But whether you like this representation or not, the key point is we've got to actually make a positive, proactive thing of what's cool, what's nice, what's exciting, what's fun. Not always what's the, you know, he's got a nice scroll of paper, which I rather liked here as well. So another thing I obviously recognize is that much as we'd like to change everything instantly on day one, we've got to mesh with today's education environment. And, you know, that means training teachers, getting expectations, skills, delivery, confidence up. It means technology that's actually around, although that's in many, you know, as we're hearing from Chris, not in every part of the world, but technology is marching forward very, very readily. It also means traditional setups like schools. Now, many people in this room and elsewhere may have views about how the structure of schools and education should change and ought to change and is wrong and is 19th century and everything else. All those things are important, but that's what we got today, and we need to make sure we can deliver in those kind of environments. So I think that's an important part of making this change, hopefully without you know, kind of damaging the vision too much. So what progress have we made? Well, when we launched computer-based math about 2 or 3 years ago, we set out to manifest this vision. And I think one of the things I've noticed in the last year particularly is the discourse is definitely changing. I'm hearing this idea that the subject might have to be looked at. I'm hearing words that we're using a lot and that other people have used around us appearing all over the place, in different places, in different countries, in different conferences. So I think there is starting to be a movement where people understand that the subject needs looking at, the change needs looking at, etc. And I'm quite pleased with how that's gone. The other thing we did is to start to build a curriculum. And this has been a you know, thing that I've really wanted to get going on, and I think we've made a really good start on that. And you know, the aim here is to build out a complete math curriculum, or at least the core of that can be changed in all sorts of ways. We're not trying to lock everything down, but actually building this out, just one version of that is actually very difficult and needs, and part of the problem with that is, you know, all the people involved in doing that have been traditionally educated, like me, right? So you've got to figure out, hang on just a moment, are we doing this because it was just the way it was always done, or is this really the right thing to do? Or is there a better way to do it with the same components, etc.? So there are many things we need to figure out to do that. I think the other piece of progress that's come along with that is frameworks. I mean, there's not much to see for that, but actually working out what does it mean when you have a computer by default? Intellectually and practically, what does that deliver? How do you think about it? What are ways to think through how you set these things up? I think we've in fact been developing a lot of those over the last year or two rather successfully. So one of the ways we think about things is sort of how they're divided between activities, lessons, topics, modules, and modalities. We've got this own little language that we've ended up developing. And you know, activities and lessons and how they mesh, what are the topics? Modules are the sort of groups of lessons which answer a particular problem. Modalities are the ways you deliver that. You know, is it the teacher talking? Hopefully not most of the time. Is it students getting data? Is it them sending data to the teacher? Is it, you know, what is it that you're doing? What's the way of your actually, are you investigating or not? And so we have a kind of three-dimensional version of that we'll talk about. Another piece of progress is Estonia asked us to look at probability and statistics in their school curriculum. And we've been working hard on building that out. And I think we have some Estonians here to represent what we've been doing, which is great, and we'll hear more from them later, and we'll see it. And I think it's, you know, it's very interesting to see how much has changed, what we've had to do to achieve that. But that's another great piece of progress. We're actually manifesting a real thing that we will be able to see later in this conference. Now, I wanted to come onto my surprise list. So as we've been doing these things and making progress, I have a whole bunch of surprises that, to me, have been surprising. So this idea that the discussion of delivery always predominates subject matter. That's something that surprises me. People say, well, you're talking about this, you have to go around several times. You're talking about the subject of math, but math is just a fixed thing in life. That's what, it's just there, right? It's like the world is spherical. There's maths. No, we've got to talk about the subject, and that doesn't happen. The other thing that's strange, and maybe people here can help me, is finding a coherent list of outcomes. What is it that we're trying to achieve from 10 years of math? Right? We have really struggled with that. And one of the things we will show later, and we have a whole session on this, is outcomes. What are we trying to do with outcomes? We have a list that we want to show you, but we are very interested in other suggestions from that. How different the vision makes stuff come out. I didn't know at the beginning of this project. Maybe when we build stuff, it'll just look the same as everybody else's stuff. No way. I think it looks very different. And in fact, more different even than I thought. The other thing that, particularly when we were working on the probabilities and statistics Estonian project, we found is there are some ideas in math that are surprisingly confused. I mean, there were a bunch of us who were fairly highly trained maths people sitting there thinking, you know what, I don't get what this means. The definition of this, you look it all up in various different places, it's all muddled. It's not very surprising if our students are pretty muddled, if what they're being fed is pretty muddled to start with. So, I mean, that's something, and I think, by the way, the script of maths, so to speak, can also cause that as well. Here's another thing that I find amazing, and only occurred to me fairly recently. Abstraction is used backwards. So the point, what normally happens in math class, people are presented all these abstract things. You can do this, you can solve a quadratic equation for whatever reason, right? And that the abstraction is used to scare people off the subject. Actually, abstraction is a fantastic tool inside math, right? It's the way that you take lots of apparently totally disparate situations and you turn them into something that you know how to solve. So we're totally using abstraction the wrong way around in most cases. Start with the real thing and move to something that's abstract that can help you solve the problem. And again, we talked a bit about computers used the wrong way. Let's not start with the assumption initially that the main point of the computer is to just replace a teacher. Let's start with the assumption the computer's there to do the calculating. There may be many things we can do to improve the delivery with computers, but that's sort of not the initial assumption we have to make. And the other thing is this thing that confusion predominates disagreement. So the thing people told me at the beginning of this project is, the whole world is going to disagree with you forever about this until you can, it'll be a very, very slow thing to get. I haven't really found as much of that as I was expecting. What I found is profound confusion. You talk to endless governments and you say, why are you teaching math? And they say, I don't really know why they're teaching math in the end. Well, they taught it because, and you say, why? Why are you doing the quadratic equation? Why are you doing the long division? Why? And the answer is because it's good for you. They don't really know, right? So I actually think that's good news in many ways, because I think that we need to help people understand what we're talking about. It's not necessarily a huge battle. It will be in some cases. It's not. You don't have to pre-assume that. Also, how deep this math versus math chasm actually is. And that is pretty obvious. And the reason part of this is also surprising is because one of the reasons I realize we are very central in this is as Wolfram, we've been kind of in the middle of math in more ways than I think any other organization on the planet for 25 years. We just celebrated 25 years of Wolfram. So we're kind of the math company. So the fact that I'm having all these surprises in these ways is in itself quite surprising, I guess. And one thing, by the way, just to hark back to our 25 years, I found this quote from Steve Jobs when Mathematica first came out in 1988. And I showed this actually once before, but I want to show it again because I think it's such a good quote. Mathematica will revolutionize the teaching and learning of math by focusing on the prose of mathematics without getting lost in the grammar. And I only recently looked at this in the last couple of years. But I think, typically Jobs, rather ahead of his time. But I think it's a rather interesting reflection on what I see as what we need to do with computer-based maths now, in the sense of what he saw Mathematica could in principle do, but has not really done in the school level in most places, in the sense that it hasn't managed to make this reform as yet, which is what we're trying to fix. I wanted to address quickly why now. People have been trying to reform math for a long time, and some good things have happened. Why do I think now has a particular resonance to it? Well, I think there's sort of three reasons. I think the impetus is very strong. There's a lot of money being spent. There are a lot of governments who know things are screwed up. There's a lot of dissatisfaction. So I think there's a lot of push to make change. I want to actually jump to interface. I think that the interface with computers is much better now than it's been for a long, long time, and it will continue to get better. I think that interface allows people to interact much better, and it allows this thing to get going much more easily. There isn't a big gap that's necessary there. And the third thing I wanted to come to is ubiquity. Obviously, as we've heard from Chris, there isn't true ubiquity of technology, but there's surprising ubiquity of technology coming. The technology isn't, in most cases, really the problem. And one of the things I'm very pleased about is we have Ibn Upton from Raspberry Pi today, and we have Raspberry Pi, which has made a great improvement in ubiquity by having a $25 or $35 computer, depending on the setup, which really a whole computer, and we'll hear, of course, much more later about that. And it's really exciting to have that ubiquity. But this morning I'm going to announce something that adds to that ubiquity. I'm going to call it ubiquity squared, which is that we are bundling, going forwards, Mathematica for free on the Raspberry Pi. And actually, I'm going to add a ubiquity cube to that, because we're also going to bundle a new thing that we're announcing today called the Wolfram language. And the Wolfram language, in a sense, is a manifestation of the language that's existed in Mathematica, and it has a nice little wolf logo. The idea is to give people the idea that there's a language you can speak, that we think we have a very nice language for representing ideas. And, of course, with Mathematica, they're also tied into computation. And so that is also going to be bundled on the Raspberry Pi, and I hope will really improve the ubiquity of provision both in many of the developing countries that Chris has been talking about, but also for everyone to use. And remember, there are many reasons. I talk about ubiquity here. Raspberry Pi is also fantastic as a way to attach to devices, and to be able to program that to happen is also really exciting. And we'll see some of that later in the technical session. So I don't want to steal more thunder there, but I'm really excited about this, and I think it can really help. Actually, one more thing I want to say is the tying together of maths and coding. Because we talked earlier about the connection between maths and coding. I think that this is a real manifestation of that connection, and it will be really exciting to see how people excited about coding can get excited about maths. So to round off, last year's summit, we talked about what are the steps to delivering computer-based math education worldwide. And we've started and we've worked with Estonia and others to manifest that, and I think we've made great progress, which we'll show today. This year's summit, how do we deliver improved life opportunities worldwide, including for the most disadvantaged children, by cooperating on a fundamental rethink of the maths curriculum? So I think we feel like we've got the impetus and the understanding from the last few years to be able to really move this forward and zoom it out to a big overriding project. Just quickly, the running order we've picked for the conference, sort of in rough order, it's why math, today's tools, how do we manifest change, specifics on solutions, case studies, and next steps. And one of the things I think is very important is we want to think of actions that we can really all cooperate on after the summit, and we want to come back to that, and it's a very important thing that we come back to through today in particular and tomorrow. My big message here is when you've got automation, you need to stand on it. And one of the challenges for education has been the idea that somehow when you get new automation, you've got a kind of a choice. Do you teach everyone what they were supposed to be doing anyway? They'd always done in the past, which goes around the new automation or mechanization. Or do you decide, you know what, that was the mechanics of the moment. Let's take the new automation and stand on top of it and go further. We have that opportunity now for STEM, for maths and for STEM, like never before, and that's what we really need to together do. And I think, back to the 25 years, what will maths look like in 25 years? I think there are two choices for math. It will either die as a mainstream subject, or it's got to turn into something like computer-based math. Those are the options. It'll be classics of the future. And I don't think it should be that. And I also think that the countries that first go onto this, the countries, the districts, the schools, the states, whatever granularity you want, will leapfrog others in their societies and their ability to get people into STEM and all the benefits that has. I look at this a little bit like the introduction of universal education. Universal education is great for everyone who does it, I think, if it's done the right way in particular. But the countries that did it first got a huge boost from that. The UK, for example, did really well out of having early universal education. And I think the same will be the case for this fundamental reform of math. The places that do it first will gain hugely. And so I'm hoping this 25-year is an outer bound rather than anything sort of more mainstream. Outcomes from the summit. I think we want to sync on the concepts, fill out the details, scale up, and plan for implementing in each world situation and each of your situations. I think that's a key thing to sort of keep in mind as we're going through. So let's all help to unscramble maths over the next couple of days. Thanks very much.